Mainly we look into numericals only. I've only prepared numericals because that's the trickiest part. Theory you can prepare, it will be easy. So let's just first look into, let's have a quick recap on whatever we discussed. So each module, whatever topics we discussed, I've just noted it down so that for your exam, while preparing for exam also, you can just go to these, like you can look into the heading and then you can try recollecting what was the content that you learned in that, or the important formulas which you learned. So first one, the first module was very simple. We just looked into all the general aspects about what are the issues which are there. Why do we need to plan for why do we plan need to plan urban services, the water supply, sanitation services? What is the need of planning these services? Then so we just went into the basics of water sensitive planning. What are the advantages? What are the diseases which can be caused? And then in module 2 we went into a bit more detail. We started with water demand prediction and management. So we even saw in all these population prediction methods, we because for while designing any utility or any service or any planning facility for that matter, we first need to predict for how many people are we designing this for, because most of these facilities would be designed to last for a long duration. Like we learned about design period, that is how long will a facility last. So based on that, based on the design period, we also project what would be the population at that particular point of time so that we can design the facility accordingly. Then we also saw into what will be the fluctuations in demand by usage based on the land use, land cover, usage. We saw into different factors which lead to these fluctuations in demand. We also saw what is the role of government. This was in very briefly we saw over here. Later in the later one of the modules, we saw went into the details on what is the role of government. Then we also saw into the cost of water supply. What are the different aspects which are there? The capital cost, the direct cost, the indirect cost, the maintenance cost. So again, here we very briefly went into this, but then again, details we learned in the later module. So then in module 3, we started going into some more calculations where first we started calculating rainfall runoff coefficient. So how do we define runoff? What is the tool that we use or instrument that we used? So we also saw Voronoi diagrams or Thesian polygons, which are used to demarcate an area and then find what is the runoff which is there in that particular region in order to find what would be the surface water. Then we saw what are the properties by which water percolates down, or how does the groundwater yield. So yield is nothing but how much can we get from that particular groundwater source. So how does the groundwater yield changes, or what are the surface water intake, so the different surface water structures which are built so that we can intake the water. So that was about module 3. And module 4 we went into pumps, so the different types of pumps. So how do we size pumps? So in that we saw what is the to calculate the pressure in the pumps, the different factors we calculate. So we always look at the suction lift which is there, that is the amount of work done in order to lift the water from a water body or a surface water body. And then we have the discharge lift, which is the pressure or the discharge head which is needed so that we can pump this onto an overhead reservoir or an elevated reservoir. And then you also have a friction head or the loss in head due to friction, which would be during this conveyance from from the surface water body to the overhead reservoir. During that period, there might be some amount of frictional loss also. So these are three aspects which we learned. So we have suction lift, discharge lift, and we have the frictional the loss in head due to friction. So all these factors, based on that, how do we size what is the total pressure that is needed in the pump? Then we also saw service reservoirs. What are the properties of service reservoirs? This the shape, like we saw into the rectangular shape reservoirs where it is used, or the most common circular shaped reservoirs, and why is it more advantageous. So all these we learned in our module 4. Then in module 5, we started looking into the distribution system. So till here, we were looking in separately at each factor which is involved, and now we are going into an urban scale over here. We are looking at the distribution system. How do we convey water? What are the different pipes, joints that we need? And then finally, we came to the distribution network design. So the grid system or the radial system. So what are the different systems that we use in order to distribute water. So this was about water supply. Then in module 6, we went into water quality. How do we test the quality of water? What are the different chemicals that can be there? So we saw that certain chemicals are very harmful for human consumption, and it has been causing even skin cancer and many other harmful problems to people. So how do we check the quality? What are the different checks? So we learned about color test, odor test, then advanced chemical test also. And then we looked into water treatment. What are the different water treatment methods? So the different levels of water treatment. So we learned there's a sedimentation, filtration, coagulation, and then finally you have the there's a rapid gravity filter, and then you filter the water. So at an urban scale, what are the different processes that a normal water undergoes before it is supplied through a distribution system? So we learned into all those water treatment methods. So that was about our water supply part. And then when we went to module 7, we started looking into the sanitation part. So this was like, so it's a 12 week. So by first 6 modules mainly looks into the water supply part, and then from week 7 we are looking into sanitation. So sanitation, we looked into the basics of sanitation, uh, the the basic requirements which are there, or the basic health requirements, and the overall, we went into a very overall very high level overview. We did not get into the details over there. And then we looked into the sewage system. So how are sewage system designed? uh, so we looked into the different layers, like we have the ODF protocols, where we have open defecation free regions, and then we have ODF plus, which means there's collection of sewage, as well as proper maintenance and disposal of sewage is also taken care in ODF plus. And then you have ODF plus plus, where you have, it's a more advanced version, where you even look into how the sewage can be treated, and then how they can be reused, or what are the so more advanced methods. We looked into that. So these are the three protocols which were important in this lecture, where you have the ODF protocol, ODF plus plus, and ODF plus and ODF plus plus protocol. Then we saw what are the different types of sewage. So we learned into some technical terms, like what is sewage, what is sewerage, what is a sewage network, so what is a sewer. So all these so these terms which are used in the sewage networks, all these terms we also looked into those. Then we also looked into what the drain. Yeah, so in the next module 8, we looked into the water carriage system and sewage layout. So in this lecture, in this module, we also saw into what is a combined sewer, what is a separate sewer, and what is a partially combined sewer. So if it's a separate sewer, your stormwater, just, yeah, if it's a separate sewer, then your stormwater and the sewage, which is collected, the domestic waste or the effluent or the industrial waste, which is collected, will go through separate sewers. But if it is a combined sewer, then it will be going through a single pipe. So the issue with the combined sewer is that in regions where there is heavy rainfall, this combined sewer would be easily full, and we'll have to design the sewer. The diameter of the sewer has to be designed to cater to this heavy storm water also, which means you'll have to spend more. And when there is not adequate rain, then the sewer will be very less. So because of this, we go for a partially combined sewer, where we have or a partially separate sewer, where we have the stormwater is allowed to enter the sewer lines. Not 100% of the stormwater is allowed to enter. A percentage of stormwater is allowed to enter the sewer line. So when there is heavy rainfall, it can be diverted through additional sewers also. So that was one important aspect which we learned in module 8. Then we learned about different stormwater drainage planning. How do we plan stormwater drainage? So we saw the different drainage systems, where you have the radial system, where you have the grid iron system, or you have the rectangular, the perimeter system. So all these different systems we saw. And then in module 9, we started going into sewer design. Or where, by sewer design, we mainly talk about the diameter of the pipes. How much should the diameter of the pipes be? So we saw the Manning's equation, which we design, which was mainly used in order to design the diameter. So this Manning's equation was used for both water supply pipe design as well as sewer pipe design. When it comes to water supply pipe design, we assume that the storm water, uh, yeah, so it can be, the pipes can be 100% full, but when it comes to sewer design, we always, or the sewerage, in the sewerage network, we always assume that the pipe is never 100% full. It'll only be partially full. But for our calculation purposes, we will assume that the pipe is 100% full. Yeah, that was about, yeah. So in order to design the sewers, so if it is a combined sewer, then we need both surface runoff and we need the sewerage, right? So for that, we also saw different methods of estimating runoff. So we learned different methods like time area method, unit hydrograph method, then also time area unit hydrograph, and yeah, how do we convert it into a hydrograph or a hydrogram, and then we convert. So different as methods we learned over there in order to estimate the surface runoff. And then we learned about the sewerage network design. So this was yeah, this we've already, I just explained that. Yeah, so now coming to the last three modules. In module 10, we looked into different sewer appurtenances. So by appurtenances, we are mainly talking about the manholes, the traps which are there, the gates, the flap gates, the so backflow prevention devices, which is flap gate is an example of these backflow prevention device, and different pipes which connects these. So we learned about butterfly valves, pressure valves. So all these valves and all those we discussed. Then we saw stormwater drains. Yeah, how do we drain stormwater into the surface water body? Then we also saw into sewer maintenance and cleaning. So what are the different methods we use in order to first inspect the sewage? So we have cameras or CCTV cameras which are run through the sewers to inspect the condition. And then for cleaning, we learned different aspects. So we learned hydraulic methods of cleaning, mechanical methods of cleaning, like a vanilla, a ball, a cloth ball can be put into the sewer and then cleaned it. So before that, we had to see the previous one. Before that we saw how do we test whether the sewer is airtight, or sorry, watertight, like there's no leakage. So we have a water test for that, and we have an air test. And to see whether there's some obstruction in the sewer, we pass these balls, so concrete balls, so concrete rollers are passed through the sewers. And once that's done, the sewer is kept in its place. So backfilling. So that was, sorry, I missed it over here. In the sewerage network design, we also saw how backfilling is done. That is, after we do all the water test, air test, and this roller test, to ensure that there's no leakage, and to ensure, so the roller test is done to ensure that there's no obstruction inside the sewer. After that's done, you place it inside the sewer on the ground, and then you backfill it so that it stays in place. So we learned about that also. So that comes in our laying of sewers. Again, we discussed that. And then comes a utility corridor, where we learned about certain utility corridors where you have certain electrical supplies, the sanitation pipelines, everything is channelized in one corridor. So usually it's done along the road network, so that under the roads you can have a utility corridor where all these. So if you want to do some maintenance for all these services, then we just have to open out one region. Whereas otherwise, if it's just simply dug on the ground, then you'll have to keep digging. So we discussed, and then the last two lectures was again last some module 11. We looked into some treatment methods, so sewage disposal methods, then natural methods of sewage treatment. Art. So this is art. So this one mainly has all these artificial methods of sewage treatment. So it has a lot of bioreaction, bio terms, and all. How do we yeah, how do we use these bioprocesses? What are the layers, or what is the procedure in which we do? So we went into those details. And finally, in our module 12, which we discussed day before yesterday, we saw into groundwater recharge and urban flood management. So this was mainly about urban flood management and the softwares that we use to manage flood. So we learned about HECRAC software, and the different input file types, and the workflow that we follow for this. So that was a very quick overview of all the contents which we have learned in this entire course. So once you have, again, as I said, right now, this might be a lot of information to you, but I guess once you have finished studying all the modules, maybe you can just use this PPT in order to just look at the heading and then see whether you're being able to recollect whatever you learned in that chapter. So just a quick tip, the factors that you might see is that if there are some formulas, if you can recollect those formula, for instance, when it comes to designing of pipes, it's always Manning's formula or Hazen Williams formula. So that also we have discussed. And then when it comes to all the to find the yield of the well, so you have the recuperation test. So in that case, you have the Thiem's formula. So I mean, I'm just saying this like this. So if you're confused, don't worry. Once we finish all the problems that we are doing today, I think these formulas again will get reinforced in your head. So one idea is that when you're going through each lecture, just make a note of the formula so you can probably keep a separate paper where you just write down all the formulas so that you can, when you're solving problems, it would be useful. So one thing can be formula, and then if there are any problems in that particular module, you can quickly go through that. So that will again be solved in this. And then you can make a note of any all these if it's some biological treatment or mainly the main content. What is the main content in that? And if there's something that you need to remember, like some technical terms which you need to remember. For instance, the design period of a pumping station is 15 years. And what are the air this one rainfall is always measured in height in millimeters, and we use a rain gauge to measure it. So there are certain technical things which you need to discuss. So all these technical aspects which you felt or which mostly we have discussed all the important aspects in our weekly sessions itself. So those important aspects you can write it down. So keeping a small 1-2 page note like this would be very useful just to brush up on the day of the exam. So it would be good. So yes, so now let's get into the problems. So these questions I've mainly taken them from the previous year question papers for NPTEL as well as GATE questions, which have been which has come based on these topics. I've taken those questions. So your exam format is a bit different. So here again, you will have multiple choices, but these questions did not have a multiple choice where to enter the value inside. So because of that, I've left the question as it is, but because we're just solving it. But just to remind you that your exam format for this NPTEL course will have multiple choices and no 5 mark questions would be there. It'll all be maximum 1 mark or 2 marks. I think a separate mail has come to you regarding the exam format, right? Did you get a mail regarding that? No. Hello. Am I audible? Hello. Sorry, ma'am, I'm in hospital, so I'm. Oh, okay, okay, fine. Yeah, yeah, that is okay. Yeah, I just wanted to check that I'm audible. Yeah, if I'm audible, then that's good. Okay, so yeah. So Aishwarya, you're around, right?
Ma'am, just give me 5 minutes to settle down, ma'am. I'm just hearing. Now, I'm not doing the calculations right now.
Okay, okay. I'll give you 2 minutes. Settle down because it'll be easier if we do the
Yes, ma'am.
calculations together. Yeah.
Yes, ma'am.
Yeah, yeah. Okay, Aishwarya, let me know when we can start, okay?
Ma'am, just one more minute,
Oh,
ma'am.
sure,
Just
sure, sure. Take your
settling
time.
down.
Just let me know.
Yes, ma'am. Ma'am, we can start, ma'am.
Okay, great. So yeah, so let's go to the first question. So the first question is a real estate project on a 15-hectare site contains 8 high-rise buildings, apartment buildings, each with ground coverage of 2% of the site area and houses a residential population of 18,000. 40% of the site area is for landscape gardens and parks. The rest of the area is for roads and open parking. The site experiences rainfall of 1,580 millimeters annually. So there's some hint. Okay, use the rational formula Q is equal to CIA by 360 in order to find the runoff, and the coefficient of runoff is given to be 0.15 and 0.65. So we've been asked to answer three questions. The first one is the average surface runoff from the landscape area and the roads paved area after heavy rainfall of 150 millimeters in 2 hours corrected to two decimal places is. So let's do that. So we've been asked to find the surface runoff, and for surface runoff, it's already given in the question that we will be using the formula Q is equal to CIA by 360. So we just need to use this formula, but before using the formula we need to, so okay, so in this C is the coefficient of runoff, and coefficient of runoff we have two, so we have a landscaped area and then we have paved area. So for both we have different coefficient of runoffs, which means we'll have to do them separately and then add them up in order to find what is the total runoff. So which means the area of landscape, the landscape area, the total area which is landscaped, and the area where there is roads and pavement will have to be separately calculated. So let's find that. So first let's look at what is the built area. So the built area is given to be, so there are 8 high-rise apartments, each having 2% of the site area. So 8 into 2% into the total, it's a 15-hectare site. So 2% of the 15-hectare site. So this will be the built area. So built area would be 8 into 0.002 into 15. So how much is that?
Point 0.24, ma'am.
Very good. Yeah. So it's 0.24. So it's no, it's 0.02 into, no, it's 2.4. No, not 0.24. It's only 0.02, 2%. 2
Yes,
2.4
ma'am.
hectares.
2.4
Yeah,
hectares. Yes.
2.4 hectares. So that is a total build area. Now in that landscape area is given to be how much, 40 percentage of the site area is for landscaped area, so which means 40 percentage into 15, this will be landscape area. So how much is that? Does that work out to 6 hectares?
Yes, ma'am.
Okay. So now for roads and parking, so it's just given the remaining area. Rest of the area is for roads and open parking. So we'll have to subtract. So for roads plus parking, the area would now be total area, which is 15 hectares, minus the 4 which goes for build up area, plus not 4, sorry, 2.4. I wrote it wrong. Yeah, Partha, very good. 6. Yeah. 2.4 plus 6. So 15 minus 2.4, how much does this work out to?
6.6.
Very good. 6.6 hectares. Yeah, very good. So now, so we have got A for to find in the formula to use CIA by 360. C is the coefficient, the this one coefficient of runoff. I is the intensity of rainfall, and area. This is the area. So A part is done. C is already given in the question. Now what is I? So I, let's see in the question that it's given that where is I? Yeah, so the site experiences, okay, no, this is the annual amount of rainfall. And yes, so in this question one, it's given that if paved area after a heavy rainfall of 150 millimeters for 2 hours. So which means I is equal to 150 millimeter for 2 hours. So for 2 hours, I'm getting 150 millimeters. So which means for 1 hour, how much will the intensity be? 150 divided by 2, which is 75 mm. Yeah, very good. 75 millimeter per hour. So I in this case would be, I'll write it here. I is equal to 75 millimeters per hour. So and now we can find the surface runoff. So surface runoff for landscape areas, which is QL, I'm calling it, CIA by 360. So here, what is the C which is given? For landscape area, it is 0.15. So 0.15 into intensity 75 into the area 6 divided by 360. And same I'm writing for roads and pavements, CIA by 360, which is 0.065, sorry, 0.65 into 75 into 6.6 divided by 360. So yeah, so tell me when you've completed the calculation.
For landscape, it is 0.18.
For landscape, it is 0.18, very good. And for this one, roads and paved area,
0.89.
0.89, very good, 0.89. So the total would now be 0.18 plus 0.89, which works out to
1.07.
1.07 meter cube per second. Yeah, very good. So that was the first part. So first part we are done. Now the second part, the annual total surface runoff from the site in meter cube per second. So we have been asked to find the annual total surface runoff. So this was the average surface runoff. So for average surface runoff, we use this formula by looking at this one, the like for that particular rainfall data which was given. Now to find the annual total surface runoff, we need to take the annual rainfall. So that is the data which is given over here. The site experiences a rainfall of 1580 millimeter annually. So we'll have to make use of that data. So what we have now is annual rainfall is 1580 millimeter. So which means previously, the intensity we found by taking the rainfall for 2 hours, which was given. Now here we'll take this annual rainfall data and then find what is the intensity per hour. So how do we do that? So if this is the case, then the intensity per hour would be 1580 divided by, so this is for an entire year, right? So which means for 365 days, and each day has got 24 hours. So in order to find it per hour, we'll divide it by 365 into 24. How much does that come out to?
0.18.
Yeah, very good. So it is 0.18. So that is the intensity. Now we can use the same formula. So QL would now be CIA by 360, which would be Now, that's what was 0.15, yeah. 0.15 is C into, so instead of, yeah, so now intensity would now be 0.18. So 0.18 into the area, which is 6 divided by 360, and then QR is equal to, again, CIA by 360. So that is 0.65 into, this was, yeah, 0.18 itself into 4.5. 4.5 area. No, no, sorry, not 4.5. Area was 6.6. Sorry, yeah, it's 6.6 into 6.6 divided by 360.
Ma'am, for QL it is 0.00045.
Very good. Yeah, three zeros and then, yeah, very good. 0.00045. And for QR it is
It is 0.00214.
2, huh? Yeah, so 0.002, 0.002 it would be. Good. So how much does the total come out to? 0.00045 plus 0.0021. Yeah, we need to take 21 because we have to add it, right? Yeah.
0.002595.
Yeah, 2.5. So approximately we can say, so something around 0.0025 means 2.003 we can take it
Okay.
as.
Yeah.
So yeah, that meter cube per second. Okay, so that was an easy one. Now the third one is again the same thing. It's the annual yield from the site in meter cube per year. So again, so it is per year. And by yield, what do we mean? It's how much can be yielded out or how much are we getting it from that. So if this much of water is falling monthly, and so we have this annual data. So we have been asked to find what is the annual yield. So we now know that this one point, yeah. So this one is meter cube. So the volume of water in meter cube per second, so it's like reverse calculation now, is 0.003. So now for 1 year, so this is per second if this is the case, for 1 year, what would be the volume of water that we have? The other one was rainfall, which was measured in millimeters. The what? Now we are finding the volume of rainfall, which will be there, or the total capacity or the volume of water that can be there. So in that case, we will multiply it by, so that one, the yield would now be 0.003 into this one. So in a year, there are 365 days.
5 into
So 365 into, now every day, it how many seconds are there in a day? So in one day, we have
3.
24 into 60 into 60, which is 86400 seconds. So this is, usually we know that there's 86400 seconds in a day. So we'll multiply it with 86400. So this will be the annual yield or the yield per year. So yeah, so that works out to 36072 meter cube per year. So yeah, so this maybe in our this lecture we have not learned this, but for from GATE point of view or for other competitive exam point of view, such questions are also there. So that's why I included. Maybe for this NPTEL, I'm not sure where, maybe because we did not look into this aspect in our NPTEL, but because this is a related question, I put it.
I got the answer as 94,608.
Ah, okay. Yeah, it is point 0.3. Correct, correct. It is 94,000. It would be, yeah. I took it as 0.002 and then I did the calculation. Yeah, so
Okay.
0.03, you might get a different answer. Yeah, correct. It's possible. Okay. So let's proceed to the next question. Question 2. The diameter and slope of a sewer line having circular cross section is 50 centimeter, and so this is, the diameter is 50 centimeter and the slope is 1 is to 220. The sewer is flowing full. Manning's rugosity coefficient is 0.015. The discharge in meter cube per second of the flow. Round the answer. So this is a very important question from our NPTEL point of view, because we've been I think we've done in two separate lectures, we've used separate modules, we've used the same formula and then done. Like one was for water supply when it came so storm water conveyance system. Also, we used the same formula and then did. And when it comes to sewage pipeline design, also at that time also we use. So this is a very important question from examination point of view also. So we have a circular. So what is the information which is given to us? So we have a circular pipe of cross section 50 centimeters, having a circular cross. So which means this full is 50 centimeters, and the slope in which it's laid is 1 is to 220, and the sewer is flowing full, and the coefficients are given. So we will use Manning's formula over here in order to calculate. So what we have been asked to find, what the discharge, the volume, that is what we have been asked to find. So we know using Manning's coefficient, we can find the velocity in which, or we can find, yeah, we can find V, but we have been asked to find Q. So we know Q is equal to A into V. Area into that velocity will give us the will give Q. So first we will find V, and then we'll use this formula in order to find Q, the total. Q is the volume of water. So the volume we will find after that. So V, we can use Manning's equation. So Manning's equation goes as 1 by N is equal to R raised to 2 by 3, S raised to 1 by 2, where N is the Manning's coefficient, R is the uh, hydraulic radius. So R is hydraulic radius, hydraulic mean we call it. So which is essentially your wetted area by wetted perimeter. So this one, I think you can make a note. I think when we were discussing in our, even in our NPTEL lecture, even in the live sessions, everywhere, we have mainly taken it as area by wetted perimeter. Even some textbooks show that it is area by wetted perimeter, but actually it is, there are other textbooks, like there are other books which shows that it is wetted area by wetted perimeter. So this is the actual value that we need to take. We need to take wetted area by wetted perimeter. Why I'm saying this is because most of the, so we in our lecture also we have seen some empirical relationships, and we have seen what is a percentage value we take. So while doing all that, we take the wetted area by wetted area by wetted perimeter, and then do the calculation. So I think somewhere there is some misconception, and people sometimes mistakenly take area by wetted perimeter and then do the calculation. And in this case, we may go wrong. But maybe in our NPTEL somewhere we might have made this mistake also. But recently I had a discussion with Professor Pandit, and uh, it was clarified that this is how it should be. It should be wetted area by wetted perimeter. But so let's say if it's wet, so usually it will always be pi pi by 4d. It will be like, if you have an area would be pi d square by 4, and perimeter will be pi d by 2, and 2 pi, yeah. So this would be 2 pi 2 pi r, huh? So pi d by 2, so this pi d it will be. So d and this will get cancelled. So it'll be pi d by 4. So if it is what pipe flowing full, then it's d by 4. Even if it is a pipe flowing half full, it will still be d by 4, because we have, like, if it is a half, if you're using this formula, then the wetted area would again be half, right? So we will have the area would also be half, the perimeter would also be half. So this half and half will get cancelled, and this would be there. But so because this is half and full, it cancels out, and it's always pi d by 4. But if it's any other proportion, then the perimeter would not be exactly, would not go like that. So that's why in our lecture, if you revisit the lecture, we have drawn a circle, and then we have calculated what will be the perimeter if this is the case, and what will be the area. And then the wetted area and wetted perimeter has been divided and then taken. So this was one small clarification which I wanted to do in Manning's formula. But don't worry, because mostly the questions for exams and all usually ask for full flowing pipes only, which means we will be taking pi d by 4. That's the standard which is used in most of the textbooks. If you see, that is how it would be followed. So just keep in mind that the r would usually be pi d by 4. Otherwise, and until it's mentioned that use this formula, use the formula that R is equal to area by wetted perimeter, or use the formula R is equal to wetted area by wetted perimeter. So sometimes this will be given as detail. So okay, so now let's solve this question. So in this particular question, we know, yeah, and S is the slope. So that is given to be 1 is to 220. So we can substitute the values. So yeah, so before substituting, if R is equal to, sorry, pi also got cancelled, right? Yeah, pi also got cancelled. It's just d by 4. It's not pi d by 4. It is d by 4. I wrote it wrong. It's d by 4. Pi will get cancelled. Yeah, so r in this case is d by 4. So d is point, so it's 50 centimeters, which is 0.5. So 0.5 divided by 4, which will be 0.125 centimeters. So now we can substitute in the formula, which is equal to 1 by n is given in the question to be 0.015. So 0.015 into r is 1 point, sorry, point, 0.125 raised to 2 by 3 into s 1 by 220 raised to 1 by 2. Yeah. So how much does that come out to? Yeah, so Partha says V is 1.23, very good. V is 1.23 and Q is 2.25. Okay, yeah, very good. So let me just solve that. Q is equal to A into V. That's what we know. So in that case, we have pi d square by 4, which is our A, into V. So 3.14 into our D is zero point 0.5, the whole square, divided by 4 into V 1.23 is equal to 0.22, yeah, around 0.225 meter cube per second. Very good. Shall we proceed further?
Yes, ma'am.
Okay. So question 3, design a water supply scheme for a population of 8 lakhs with the given data. The storage reservoir is at a distance of 10 kilometers from the city. Head loss from source to city is 25 meters. Considering the average demand as 135 LPCD, maximum demand can go up to 1.3 times the average demand. Pumping done in two 8-hour shifts. So pumping done it. So there's a lot of information given over here. And the for metal pipes, CH, CR, so all these are coefficients. So these are the coefficients which are involved in these formulas. We would need these coefficients, so that's why it's given. F dash is also given, and yeah, are to be used for the metal pipes are to be used for the mains. Calculate the size of the mains using all the three methods. So I put this so that we know for all the three methods how do we calculate the mains, in one question itself we can solve and then go ahead. So let's get started. So we first need to find the quantity of water, or the demand. So maximum demand, it's given in the question that assume the maximum demand to be 1.3 times the average demand. So the demand is given to be in 135 LPCD. So 1.3 into 135 LPCD will give us the maximum demand. So Yeah, how much does that come out to? Is this class recording? So this recording, I am not very sure because the other recordings I know that it will be available. This one, I'll have to check. Mostly it will be made available, but I can't guarantee you. The other sessions, I know that it will be available.
Ma'am, it's 175.5.
Yeah, very good. 175.5 LPCD. So this is the maximum demand that we have. So if this is the case, per day, so this is LPCD, that means per capita per day. Now, if you remove the per capita out, per day, what will be the demand? Will be into the total population. So population is given to be 8 lakhs. So 175.5 into 8 lakhs will be how many liters per day that we will be needing. Sorry. Does that work out to around
14
14?
crore,
Yeah. Yes,
14
tell.
crore lakhs.
Yeah. So can I rewrite it as 140.4 million liters per day? Because 1 MLD is equal to 10 raised to 6 liters. That's a very big, yeah. So I'm writing in terms of MLD. So 140.4 MLD. Now pumping is for, let me write it here. So maximum demand will be 140.4 MLD. Now we know that the pumping is for 16 hours, right? 16 hours. So in 16 hours, we are supposed to reach 140.4 MLD. If that is the case, per hour, then per hour, for 1 hour, what should be the pumping? So that should be 140.4 divided by 16. So that works out to
8.77.
sorry.
8.77.
Yeah, 8.77. Okay. I mean, I just left the figure like that. Okay. So now, so this we know. So for 1 hour, we need 8.77 MLD to be transport. The pipe should be capable of doing that. So now let's see. So we have to find the size of the mains. So now we know what is a quantity. We just need to find the size of the mains. So first we're using Darcy-Weismann's formula. So Darcy-Weismann's formula goes like, so first one, yeah, Darcy-Weisbach formula. I'm just not writing the whole thing. HL. So in Darcy-Weisbach formula, what are we essentially getting? We are finding the lift which is there, or what should be. So we first need to find the lift in that case. So HL is equal to F dash L V square by 2GD. This is the Darcy-Weisbach formula which we will be using in order to. So our idea is to find the diameter of the pipe, and we know how much is being pumped. So the pumping, wait, in not pumping, this one, yeah. So the head loss from the source of the city is given to be 25. So this we know, which means the head loss to the source, which is HL, that we already know. So that's why we can use this Darcy-Weisbach formula. So diameter is what we are finding. So this also has D in the formula. So that's what we will be finding. Now we know Q, but we do not know what V is. So we can write this one Q in terms of, like we did as we did before. V is equal to Q by A. So Q is equal to A into V. So let's do that. A into V. So which is, so we already got this 140 by 16, which is 8.8. So 8.88, which is our V. I'm just doing this first. And what is the area of the pipe? Huh. So area we can convert it in terms of, that is what we are trying to find, right? So we have to convert it in terms of, uh, yeah. So This one 8 point, yeah, this we can keep, yeah. So one thing which we need to do over here is that this is in million liters per day, sorry. This is in liters per day, right? And to use this formula, we need to convert it into meter cube per second. So that conversion we need to do first. So V is equal to 8.87, but we also need to divide this by 60 into 60 or 3600, and then multiply it with 1000 so that your million liters gets converted to meter cube per second. So because it's 10 raised to 6, right? Uh, yeah, million liters is 10 raised to 1 mld is equal to 10 raised to 6 liters, and 1 meter cube is equal to 10 raised to 3 liters. So there's a 1000 which is remaining. So we are multiplying it with 1000 and then dividing it by 3600. So that works out to, yeah, so how much does that work out to? 140 point, yeah,
43.
yeah, 2.43, very good. 2.43 meter cube per second. Very good. So we have got B. Now A is what we have to find, but we can simplify this formula and then write in terms of A itself by saying that if A is equal to pi d square by 4, if we put it over here, it'll be F dash L Q square divided by 2 into G into D into this Q, it'll be Q by A, no? So it'll be Q by A, so that A I'm bringing it here. So pi D square by 4, the whole square. So this can easily be simplified. And is F dash given in the question? Yeah, F dash is given in the question, so we don't have to worry. So this F dash L Q square by 2GD uh, pi by 4 the whole square. So this square, I'm only separating it to pi by 4. And because there's a d over here, I'm combining this d. So this becomes d raised to 4. 2 into 2, 4. Plus this 1d, so d raised to 5. So formula becomes f dash l q square by 2g pi by 4 d square pi by 4 the whole square. So this formula, I think you can make a note and keep. So in our lecture also, we have done the derivation, but all the problems whenever we are doing, we are always done using this formula, and that increases the complexity. So because most of the questions will not give us V directly and we'll have to find it from Q, you can remember this formula itself. So now it's a direct formula substitution. So HL, we know it is 25. So 25 is equal to F dash is given in the question to be F dash
Point
is point, yeah, 0.012, correct. So it will be 0.012 into, now L is, yeah, so L is basically the distance to which we need to transport it. So L is 10 kilometers. So 10 into 10 raised to 3. So 10, I'm just writing it together, kilometers, into V is or Q was 2.43, yeah, 2.43 the whole square divided by 2 into 9.8 into 3.14 divided by 4 the whole square into d raised to 5. So we'll get our answer in d raised to 5 now. Okay, so I'm just giving the answer out right now because already 1 hour is over and there are some more questions which I wish to discuss. So maybe if it's just the calculation, I'm sure you'll be able to do it. So this one works out to around through 2.36. So d raised to 5 will be 2.36. So if we get d raised to 5, then you can take the fifth root of this one and then we can get d, which works out to around 1.8. So why I jumped into this is that, so the value that we're getting is 1.8. But in the question, it's also mentioned that head loss. Yeah. So we need to, yeah. So here it's mentioned round off to a maximum of 3 to 4 decimal points. And the final answer to be based on commercial availability. For instance, 1 meter, 1.2. So that commercial available pipe sizes are also given over here. So this is something which we usually tend to miss. We might get that value, and to our surprise, this value will also be there in the option also. 1.18 will be given in the option, but this part which is there in the question we might miss. So it's already mentioned that we need to check with the commercially available pipes and then round it off to that. So in this case, since we got 1.18, the nearest commercially available pipe is 1.1. The next higher value we need to take, because if we take a lower value, even if it was 1.1, we cannot take a lower value because this much of quantity has to go through it. So we need to take a higher value. So we always take the upper cap, not the lower cap. So 1.25 meter should be the diameter of the pipe. So that was with Darcy-Weisbach formula. Now we'll go to Hazen-Williams formula. So Hazen-Williams formula, so the formula goes that V, again, Hazen-Williams formula is again used to find V. So V is equal to 0.85 into CH, which is a coefficient, into R raised to 0.63 into R, which is a hydraulic radius, and then slope H, which is 0.54. So this is the formula. And CH is given in the question. It's given as 130. So 0.85 into 130 into R, which is D by 4. So D is what we are interested to find. So we leave it as D by 4 into, raised to 0.63 into S, which is the slope. So S, we need to find S. So we also know that S is equal to HL by L. So which means where HL is the head loss due to that transmission. So whatever loss is there divided by how much of length it's being transported, that gives us the S value, or the hydraulic gradient line. So S is essentially the hydraulic gradient line. So HL we know it is 25, divided by L we know it is 10 kilometers. So 10,000. So that comes to around 0.00 10,000. Yeah, 0.0025. So 0.0025, the whole raised to 0.54. So this is how that works out to. Again, so if this is the case, then we need to find D. So again, we'll have to do some cross multiplication and then find D. So yeah, so no, so sorry, V we did not substitute V. So V again we know it is Q by A. So Q is equal to again 2.43 divided by A pi D square by 4. Sorry. So D will be there in LHS and RHS. So this would be 0.85 into, again, yeah, this we'll equate it to this term. And then so now we can combine D's from, so this D and this D we can combine, and then we can find D. Do you want some time to solve it, or shall we move to the next question? Like next question in the sense next method.
We can move.
Yeah, we can move, because then you can discuss more questions, right? So I'm just giving you, when you're doing, I'll just give you the answers so that you can make a note of it. So essentially you would get something like this one calculation would come up to 2.48 D pi D square by 4 is equal to 0.85 into 130 D by 4, the whole raised to 0.63 into 0.0025, the whole raised to 0.54. I'll definitely be uploading this presentation, so these calculations will be there. Recording part, mostly it will be available, but because I'm not sure, I'm not giving you a word, but mostly it will be available. Now D raised, so this calculation works out to D raised to 2.63 is equal to 248 into 4 raised to 163 divided by 3.14 into 4.3478. So finally, we will get D, after doing all the calculations, D we will get it as 1.226, which again we will round it off to the nearest one, which is there. So this is 1.22. So we can again go with 1.25 meter. So it's the same value which we are getting if you're using this method itself. Now, last one, we will use the modified Hazen-Williams formula, which is there, which is asked in the question. So modified Hazen-Williams formula goes as V is equal to 143.5534 into CR into, so this is the coefficient that we will be using in this formula, into R raised to 0.6575 into S raised to 0.5525. So this is modified Hazen-Williams formula. So again, the method all goes the same. We will find Q is equal to, so for this one, we will write it as Q by A, and then we will write Q is equal to, or A is equal to, where A is equal to pi d square by 4, and Q is equal to 2.438. And then this one, R, again, we will write R as d by 4. And then, so rest all substitution becomes the same. So if you notice, it's only the or the exponential terms and the CR. So CR is also given in the question. So CR is equal to 1. So we can neglect it. CR is equal to 1. So we'll do the calculation, and again, D in this case will also come up to 1.6 something. So again, by rounding off to the nearest commercially available diameter pipe, we will get 1.25 as the diameter. So you will definitely not get the exam will not ask you to find through using all the methods. It will specify which method you need to use. So most commonly which is used is either Darcy-Weismann's formula or Hazen-Williams formula. Modified Hazen-Williams formula I've not seen in most of the questions. Like I've not seen it anywhere, but I just put it because in case it's asked, you should be able to answer. Okay, so we'll proceed to the next question. Compute the total volume of rainfall in liters that can be collected on a roof area of 1,200 square meter with the average monthly rainfall of 90 millimeters. Determine the number of days the collected rainfall is adequate for the building's usage, where the average monthly rainfall is 120 millimeter. So, okay, so there are multiple questions. So there are 3 questions here. Let's do the first one. First, let's find the total volume of rainfall. So this is something which we did yesterday. So I think we can quickly do that. It won't take much time. So we know that's the, yeah, so what is given in the question? In the question we have, yeah, so the monthly, average monthly rainfall, yeah, monthly rainfall is given to be 90 mm. If monthly rainfall is 90 mm, what is the annual? So in the first question, annual rainfall is not given, or for the first part, annual rainfall data is not given. So monthly, so which means annual would be 19 to 12. So this is in millimeters. So this is 1080, which will work if I'm converting it into meters, it's 1.08 meters. Now, we've been asked to find what is the total volume of rainfall. So we need to, and this is the roof area. So this is what we did yesterday. If this much water is falling, this multiplied by how much area the water would be falling, we will get. So the total volume would now be our 1.08 into 1,200 square meters. So this is in meter square. This is in meter. So this will the answer, final answer, whatever we are getting will be in meter cube. So I think that calculation can be done. I'm not doing the calculation. So now the second part of the question asks us to find determine the number of days the collected rainfall is adequate for the building's usage. So when such a question is asked, we first need to find what is the daily usage. So it's given that the average daily, okay, and also the average monthly rainfall is now 120 millimeters. So this was 90, but now 120 millimeter is given, and the consumption is given to be 135 LPCD, and the roof area is also changed to 1,000 square meters. So I've just clubbed all these questions together, which are of the same type. So using the same method, we can find what will be the amount of rainfall which is collected. So again, it would be in this particular case, I'll do it here only. So it'll be 120 into 1,000 square meter into 12. Sorry, this is average monthly. So into 12 also. So basically it's 120 into 12 into 1,000 square meters. So that works out to around 1440000 liters. You can just make a note of that. And now we need to find the second part, which is the new part. We need to find the daily water consumption. So daily water consumption, it's given 135 LPCD. So using the similar one, 135 into 135 liters per capita. So how many people are using it? It's given that it is used by how many people? How many people? Household with 5 members. Yeah, 5 people are using it. So 135 into 5. So which is around 675 liters per day. So number of days that we can use would be, so it's just basically the total water collected divided by the daily water consumption. Daily water consumption. So the previous value 14400, which we got before, divided by 675. So that comes out to around 2133.3 days. So if you get something like this, we will have to say it is 2133 days. So that was the second part. This I'm just going very fast because we just did a similar problem yesterday, day before yesterday. So now this third part is that consider a situation of 5,000 liters storage loss. So now this is new. So you've got a 5,000 liter storage loss due to leakage, and the household size is now reduced to 4. So now how much will be there? So what happens is from this 1,400 we'll have to, sorry, 14, yeah, 14,400, we'll have to subtract 5,000, and also something else is also changing. Yeah, per capita demand. So that will now be 135 into 4. Instead of 135 into 5, it will now be 135 into 4. So that's the only change over here. There's a loss, and yeah. So this can be easily done. I'll just give the answer out. It comes out to around 2657.4. So which will be 2657 days. Okay. Any doubts in this question? Did I go too fast here?
No, ma'am.
Okay. So we can proceed to the next question. Yeah. So now this is again a very important assignment question. So we have already done this in the assignment, but let's do this once more. So we have been asked to consider the following diagram and observe observations made on a 30 centimeter diameter tube well. So rate of pumping is 1,500 liters per minute. Drawdown in a test. So what? So this is essentially. So this is a water table. So in groundwater yield we have learned. So this is Thiem's formula which we will be using over here. So which I was discussing in the beginning of the class today. So for groundwater yield we use Thiem's formula. So the idea is that whenever we keep drawing water, the groundwater table bends. And by using a recuperation test, like by seeing how much time it takes for the water to come up, we can find what is the yield of the well or how much water is. So how the water will come up is because water from the nearby, from the aquifer in the nearby regions will now fill this up and the water table will restore. So that's called a recuperation test. Now here what is asked is that we've been asked to find what is the radius of influence, or because of this bent, what is the influence which is there, what will be the transmission coefficient of the well, and then what is the discharge in the well. So that's what the question is about. So essentially if we have a region like this, so so now here the bending has started over here. That means the water table has the water level so the water is being taken out only from this one, but there's a small drop here. Now, similarly, in some place over here, maybe the drop will be very less, like it might not be there. And some place over here, there won't be any difference. So after a particular point R, there won't be, this influence will not be there because you're drawing water from the well, that it will not create any problems in a certain region after a certain radius. So that is the radius or circle of influence, or the radius of influence. That's what we've been asked to find. So this is the information which is given to us. Rate of pumping is given, draw down in a test well. So the total height is 40. Yeah, so this total height is given to be 40. This is 15 because 30 centimeter diameter. And now this is at 30 centimeter and 60 centimeters. We're using certain test wells. And then using these test well data, we will find what is the radius of influence. So again, the formula which we will be using is Thiem's formula. So let's just write it down. Thiem's formula is Q is equal to Km into h square divided by h square divided by log to the base 10 R by R. So this is Thiem's formula where, yeah. So in this one, Km is our transmission coefficient. And H is the water level, the initial or the maximum water level which is there. So you see, if there's maximum water, then it will be 40 meter deep, or the depth of the 30 centimeter depth of the well before pumping. So H is the depth of the well before pumping. So this is H, depth of the well before pumping, and small h is the depth of the well after pumping. So depth after pumping. And this r is the radius of influence which we are interested to find. And this small r is the distance of the test well. So we have two test wells. So for test well 1, let's see, Q will be, so I'm just writing, we don't know what km is, so we'll just leave it as km. And H is equal to 40, right? 40 meters, yeah. H is equal to 40 whole square divided by, now in the first test well, it's reduced up to 1.5 meters. So which means this height will now be 40 minus 1.5. So that's what is over here. 40 minus 1.5 the whole square divided by log to the base 10. R is radius of influence which we are interested to find. I'll keep it as R. And small r is a distance. So this distance is this one, the small test, 30 meters. So that r is 30 meters. Okay, so this is our test 1. Now for test 2, similarly we can write q is equal to km into 40 square divided minus 40 minus, in that case it's reduced by 0.6. So 40 minus 0.6 the whole square divided by log to the base 10 r by, it's at a distance of 60 meters. So it is, now the advantage, so this is the pumping, or how much of water is pumped out, or the yield. So which will be the same. It will not change. So we can equate Q1 and Q2. So Q1 is equal to Q2. So we'll equate these two. So I'm not writing it. So if we are equating these, I'm just dividing it and then saying it's equal to 1. So then these km will get cancelled out and we can cross multiply. And so essentially we are interested to find R. So the expression would now be something like, when you cross multiply everything, will be like 40 square divided by, okay, before that, what does this come up to? This will be 38.5, and this would be 40 minus 49.4. So we'll mention that, sorry, not 49, 39.4, 39.4. So 40 square minus 38.5, the whole square, divided by, so basically these two terms I'm keeping it in one side, this term and this term I'm keeping it in one side, divided by 40 minus 39.4 square, equal to the log terms on one side, r by 30, divided by log 10 r by 60. So this one, if we calculate, that will work out to around 2.47. And this one, log a by b is equal to log a minus log b. So we can write it as log 10 r by 30, sorry, log 10 r minus log 10 30 divided by log 10 r minus log to the base 10 60. So why we did that? Now all the log terms or the r terms are separate. Now we can just cross multiply. So this will be 2.47 times log 10 r, and log 10 r is also there. So when we take this to once the back here, so 1.47 log 10 r equal to, now this would be a minus 2.47 log 10 log to the base 1060. So we take it here, it would be equal to log to the base 60 minus log to the base 30. So we can write log 10 r is equal to this whole thing divided by 1.47. So essentially log 10 r will work out to 1.983. So which means r will work out to 96.16 meters. So that's what the first question asks us to find. What is r, radius of influence? Now once we get r, we have the second one, which is a transmission coefficient. So we'll use the same formula again, and then we'll go q is equal to km into h square minus h square divided by log 10 r by r So now we know what we know what R is, and Q is also, Q is essentially the yield or the pumping which is there. So that is also given in the question. Yeah, rate of pumping is 1500 liters per minute. So if we substitute it over here, 1500 is equal to Km, because we've been asked to find the transmission coefficient Km. This is what we're interested to find. Now H is 40. We can take any of the test well. We're just interested to find any. So let's take the first one, 38.5 the whole square divided by log to the base 10. And for R now we will substitute the value which we got before, which is 96.16 divided by, so I took the test well at 30-meter distance, so it would be this. So from this we can find Km. So that Km will be, so eventually the answer would be 6.45. Okay. So now the last question asks us to find the maximum rate of discharge for the well. So maximum discharge means that, so now the water has gone up to, I don't know, so 40 minus, so some amount water has gone down. And here it's 1.5, this one we don't know how much. So maximum means all the water which is there has been yielded out, which means all the water which is there will go down, like it will be zero, or whatever you say. So here you say the drawdown in the test well is 15. So like that we can say drawdown in the well, in the actual well, is 40. That means 40 the 40 meter is the depth of the well, and all 40 meter has gone down. So we'll use the same formula. So now the only thing is test wells. So we are talking about the main well now. So the test well, we will not consider any of the test wells, but we will take the main well. So the drawdown will be 40 meters, and the distance will be the radius of the well. So the well is 30 centimeter diameter, so which means radius will be 0.5, 0.15 meters. So that we'll input this into the Themes formula and then do. So that would come as Q max is equal to Km into, so h square is, so I'll just write it. H square is h square minus 0 we will write, because we are assuming that the drawdown is h itself, divided by log 10 into r by r. And yeah, so now here Km would be, we already found Km, this is 6.45. So 6.45 we will put here. H square will be 40 square. This is 0 because it's 40 minus 40 the whole square, so that is 0. And R in this case would again be found in the previous question, 96.16, and R small r would be 0.15. So we can, so this again is a theoretical value, because never will the drawdown be 100%, or it will never go and touch this much. Like before that, some yield will be there. We will never do it to the maximum. So it's to find the theoretical, this maximum discharge is a theoretical value that we calculate. Okay, so any doubts in this question? It's
No.
clear how we,
Yes.
yeah, because this is a very important question, that's why. Okay, so now let's go to question 6. What is the, this is a very simple question. Subsurface soil area required for disposal of septic tank effluent in a dispersion trench for a population of 130 with a sewage flow of 150 LPCD. Take percolation rate as T is equal to 4. So we have learned that area for trench is equal to total sewage divided by 130 root T. So this, because this is the percolation, like based on the percolation rate, so the area required for the trench would be total area divided. So T is the time, the percolation, take the percolation rate as T equal to 4. So it is, so total sewage is also given for us. It is 150 LPCD, and population is given to be 130. So 130 divided by our 130 into root of 6, sorry, root of 4, root 4. root 4, which is 2. So 130 into 2, 260. And yeah, so this is a simple calculation. It comes up to around 75 meters square. Okay, let's go to the next question. Yeah, 75. Very good, Partha. So let's go to the next question. The minimum required diameter of a circular sewer, making use of the following data. Area to be served is 120, population is given, intensity of rainfall is given, maximum permissible velocity is given. So we have been asked to find the circular sewer, and yeah, so the impermeability factor C is also given. Which formula will we use over here if such a question is given? Any guesses? Or do we need to use some formula? So we have found different, we have used different methods or different formulas like uh, Hazen, sorry, whatever Manning's formula and all that in order to find diameter only. But in this particular question, we don't actually do we really need to use some, because we so we just need to take the storm water out. So we need to find the quantity of storm water. We don't use all the other sewage treatment, like the other complicated formulas are not required when such a question is given. So all we need to first we need to find, so we have rainfall. So we need both rainfall data. So we need to find the quantity. So you will have storm water plus you will have sewage. So you'll have to add this both up and find the quantity. And if you know the quantity, then we know that we can use our Q is equal to A into V, and then based on that, we can easily find what is the quantity that we need. So let's first find the quantity. So the quantity of water for storm water, let's find for uh, stormwater we know that we already know CIA by 360. So let's do the complicated part, which is to find for the sewage, how much of sewage is generated. So we've learned in our lecture that sewage generation is proportional to the water that we supply. So based on the water supply, we know that this much percentage of sewage will be generated. So let's say that first let's look at the water supply. So supply is given to be rate of water supply is given as 230 liters per day per capita. LPCD utsil, but it's given in a bit different way. So we'll have 230 liters per day per capita. So now how many people are using? We have 30,000 people. So which means 30,000 into 230. So this capita would be removed then. And this is liters per day. So per hour, if we want to find, we'll not per hour. This one, permissible velocity is given in meter per second. So our V is given in meter per second. So we'll have to find it, we'll have to convert this into second. So per day into second. So dividing it by 365 days. No, sorry, not hour. Sorry, day is already given. Sorry, 24 hours into 60 into 60. Yeah. So this would be the maximum water supply or the water supply which is there. Now, the assumption that we make is that sewage generated, is it given on the question? It's not given on the question, but mostly it'll be given on the question what percentage should we take as a sewage generation. But if nothing is given, sewage generated is always 1.5 times the water supply. So based on that, we can take the maximum discharge is, let's say, 1.5 into this whole value. So, okay, I'm not waiting for the calculation. I'll just give you the value. It is 133.1 liters per second. So it'll be 1 liters per second. So after doing this calculation, we will get it as 119.79 liters per second. I'm converting it into meter cube per second. So into 10 raised to 3. So 10 raised to minus 3. So 0.1198 meter cube per second. So this is our sewage. Okay. Then we need to find stormwater. So stormwater, we have done a lot of calculations using stormwater. So I'm not going into the details. So stormwater also using the CIA by 360 we will calculate. And then we will find what is the combined discharge. So this plus this combined discharge. So after we get the combined discharge, which is Q is what we will get. We've been asked to find D. So Q is equal to A. Yeah, so Q is equal to A into V. V is given in the question. Maximum permissible velocity is 3.4. So A is pi D by 4 into 3.4. So from this, if you already know Q, so this is what you will be getting Q. This added thing is Q and this one. So from this you can easily find D. So approximately that D comes up to 0.5. If you're doing, you can check the answer. I'm not calculating this because we've already done a lot of similar calculation. So 0.5 meters. Let's go to the next question. Yeah. For the given population data, estimates the forecasted population for 2031 using arithmetic increase method, geometric increase method, and incremental increase method. This one we will do. Proper calculations we will do so that you don't have to revise this again, because this is very simple calculation and very easy to do, but it we learned in our module 2 itself. So let's go, let's first rewrite this information. Oh, I didn't leave any space. Okay, just give me a minute. I'll just add a slide. Yeah. So let's rewrite the information. So we have 2001. Yeah, 2001. It's 989800. Then 2000. Sorry, wrote it wrong. One second. Yeah. So 2001, 2011, 2021. These are the years that we have. And the population in 2000, this is 98,000. 2011 is increasing to 115,000. And this is 156,000. So first one, we are doing the arithmetic increase method. So we'll find the increase. So 115 minus 98. What is the increase from 2011 and 2000? From 2001, what is the increase in 2011?
17,000.
Correct, 17,000. So we have 17,000. Then next 10 years, what is the increase? 156 divided by 75. 75? No, it's not 70. Okay, 7. That was for a different question. Sorry, I just saw now.
41,000.
Very good, 41,000. Yeah. So 41,000. Now this is, so total increase would now be, we'll add it up. Total increase 58,000. So therefore the arithmetic mean will be, so there are 2 years, 2 years we have, so 58,000 divided by 2, which is 29,000. Now we have to find the projection. So projection, the population projection they have asked for 2031. So from 2001 to 2031, how many decades are there, or how many time periods are there? three three time periods, 2001 to 2031. 3 decades are there. So m is equal to, so now p 2031 is equal to our base 98,000 plus 3 into 3 time periods into the arithmetic mean 29,000. Yeah, that's an easy calculation. Is this what you're getting?
185.
185 is what you got.
Yes,
Oh, sorry, I wrote it wrong. Yeah, it's 185. Yeah, I wrote the geometric one. Yeah, 185. Very good. Yeah, 185. So that was about arithmetic mean. using arithmetic increase method. Now let's do geometric increase method. So geometric increase method, the difference is that here we took the difference. Now geometric increase, we will take the ratio. So it will be 17,000 divided by the previous ratio, that is 98. So we need to take the difference first. So this information is required. What is the difference? That difference divided by the initial, divided by 98,000. So that will approximately come up to 0.17 itself. 98,000 like it'll be 17 divided by 98, so 0.17 itself. Then here again it will be 41,000 divided by 115,000. So that will work out to how much does that work out to? 41 divided by 115.
0.35.
Yeah, 0.355 something. So we can take it as 0.36. Now P 2031 in geometric increase method would be, so geometric increase method is base plus 1 plus the geometric progression into, sorry, 1 plus, not the, what do you call it? Yeah, 1 plus the geometric progression into the raised to the power time. So time in our case is 3, this is 3, and this is the geometric progression which we are getting. So geometric progression, we are getting two values, 0.17 and 0.36. So our geometric progression will be 0.17 into 0.36. So that will come over here. So that works out to 0.17 into 0.36. How much does that work out to?
0.0612.
0.17 into 0.36.
36.
Sorry, point, yeah, that is correct. Into 0.5 also, geometry, because you're, one second. So, sorry, then my calculation has gone wrong somewhere. Point 0.06 is what we get, no? Okay. So then I think I went wrong a bit there. Yeah, so 0.06. Yeah, so then we just need to substitute the values over here. 1 plus 0.06 raised to 3. Yeah. So that, how much does that come out to? Am I going wrong somewhere?
1.19.
So I think I went wrong a bit somewhere. It won't be 1.19. You need to get a population projection, right? So this, okay, so this question I will put it in a discussion forum only for this question. What is the geometric increase method? What is the final answer? Maybe somewhere, some value I have not taken it correctly. It should be the base. Okay. Sorry, this is not plus. This is into. That is where we are going wrong. Sorry. This is this is into, so whatever value you're getting, you have to multiply it. So if that is the case, will it come 98,000? Yeah, because it's a geometric increase, right? So into point 06 raised to,
It should be 1,16,719.5. So 1,16,720.
1,16,720 is what you're getting the answer.
Yes, ma'am.
1,16,720. Okay. 1,16,720. Okay. I'm going wrong somewhere. Yeah, this will be 1.0. Correct. 1.06 into raised to 3 into this one, right? So 1,16,720 something. Yeah. So my this value went. Okay. So if you're, I trust you. You've been calculating everything. So my calculation went wrong. So very good. Okay, so that was about arithmetic and geometric increase method. Now comes our incremental increase method, which is the most important one compared to the other two. Like most of the question papers usually ask for incremental increase method only. So in that, what is the addition that we have is that we will have an incremental increase also. So just to note that from 98,000, 115,000, 156,000. Yeah, so this, I'm just rewriting those values. This was 41,000. Now we'll have an incremental increase also, that is from the difference of the changes. So 41,000 minus 17,000. That, so here there are only two. If there were more time periods which were given, then this would just further continue. So this one will be around 24,000. So if this is the case, so average increase was 29,000, that is this one. And so the average incremental increase would be, average is it this one only, because we just have one value here, right? We don't have to take an average. If there were two values, we would have to divide it by two and then take the average incremental increase. So now using this incremental increase method is, you have the base population plus the year in which you are projecting into the arithmetic mean plus our year that we are projecting, t plus 1 by 2, into the incremental mean or incremental increase mean that we are getting. So that would be around here 98,000 plus 3 into arithmetic mean is 29,000 plus 3 into 3 plus 1 divided by 2 into the incremental mean 24,000. Sorry. So how much does that come to? So this will be 3 into 3 plus 4. So this can be cancelled. So 2 is gone. So this is 6. So this is 6 into 24,000. And yeah.
It's 3 lakh
Hmm.
29.
3,29,000. Very good. Yeah, 3,29,000. So you see, there's a lot of difference if you use arithmetic increase, incremental increase. So usually they say among all the mathematical methods, incremental increase is a bit more accurate than the other methods. Again, you remember that graph which we might have learned. Like if it is arithmetic increase, it's the graph, it's something like this, like the change with, if this is the time, the prediction or the changes are like, if the changes are like this, then we can use arithmetic increase in order to predict the changes. The change is exponential, something like this, then we use the geometric increase method, and our incremental increase method lies somewhere in the middle. So usually most places it won't be a steady change, but there will be some factors, but it will definitely not be an incremental change unless and until it's a new industrial town which has come up and there's suddenly a lot of expansion in the land use or a lot of changes in the land use, land cover usage, then there would be something like this. So yeah, so this graph also you can keep in mind. That's it. Now question 9. So we have 12 questions is what I've planned. So I hope we will be able to complete all the questions. Question 9. For a city with a population of 1.3 lakh with average water demand of 145 LPCD, determine the following. So this is a very easy question. Maximum daily draft, hourly draft of the day with maximum consumption, and coincident draft. So maximum daily draft, we know, yeah, so how this, I think you can attempt the question. How do we find maximum daily draft? Or how do we go about this question? We have done similar questions. Today also we did similar questions, so we can, I think you can attempt the question. Okay, so average water demand is 145 LPCD. First thing, convert this in, remove the per capita out, convert it into, multiplied with the population and converted it to liters per day requirement. So multiplying it with 1.3 into 10 raised to 5, So, yeah, that would be the yeah, that would give you the liters per day. Now we have learned that maximum, so this we need to remember, daily draft is 1.8 times the average monthly draft or average water demand which we have. Similarly, maximum monthly, we have learned that it is 1.5 times the annual value. So using this both, we say that maximum is hourly is 1.5 times the um, this one daily demand that we have. So using this, we will say maximum hour of the maximum day is 2.7, 1.8 into 1.5, which is 2.7 times the average demand. This we've learnt in the lecture. So that's what we will be using over here. So maximum daily draft in this case, we will easily use the formula and find 1.8 into this one, 1.3 into 10 raised to 5 into, wait, into, sorry, 145 into 1.3 into 10 raised to 5. So this is the first part. Now the second part is maximum hourly demand. So maximum hourly demand of the maximum day. So 2.7 into the average hourly consumption, which is again this one, 145 into 1.3 into 10 raised to 5. But this is per day, so divided by 24. So that will give us the maximum hourly demand. Now the last one is, what is a coincident draft? What do we mean by coincident draft? Do you remember anything? Any memory? Coincident draft? Yeah. So this is coincident draft, which is, it's either the maximum of the daily draft plus fire demand or the maximum hourly draft. So the idea is that it's the amount, what you say, amount of water which is needed, right? So you add the fire demand and the daily draft or the requirement per day plus the fire demand, or for every hour if you take the demand, and if that can satisfy that, then that. So which is the maximum of that? That's what we need to take. So if such a not exactly, ma'am, but we will be using graph. No, for coincident draft, we are not using any graph. This is just a calculation method that we will be using. So the only problem is that if such a question comes, we'll have to find both and then find the maximum. So it's a tedious procedure. So let's find the first one where we will be finding. So again, to find the maximum daily draft that we've already found. What is the maximum daily demand? How do we find fire demand now? Fire demand. So fire demand, we use the empirical formula which we used, which is 133,182 root P. So where P is the population. So this is one usual empirical formula, but everywhere this need not be correct. This can only be used for very large population. If the population is really large, then we can use this one. So here we have the population above, like it's around 1.3 lakhs. So we can use it. I think above 1 lakh, we can use this formula. So yeah, so if you're using this formula, 1 into root of 1000, 1.3 lakh, right? Yeah. So 1.3 into root of 1.3 lakh. So that I'm just doing it quickly. So that works out to 36280.38 liters per minute. Now this plus our previous demand, we need to, what is the demand which we got over here? Huh? So this calculation we did not do. So if we do this calculation, we get something like, yeah, so this one, if we do this calculation, it is 33.93 that we are getting MLD. this one, which is the daily. Now this is the hourly one. Hourly one, we will get it at around 2.12 million liters per hour. Per hour, this is the requirements that we need. So if this was 33.93 and this is liters, so million liters 36, so it'll be 33.93 plus 36 points, so we will 36.2. One second, I'm getting final values. Have I added it up or not? Okay, no, let's not check those values. Okay, I'll just tell you the method because while doing the calculation, maybe if I just give you the values, even I'm getting confused which is the value. So I'll just tell you the method. So now you get the demand. So the total demand in this first case will be, you will add this up and then take. So the other one, the second one, where you need to find the maximum hourly demand, which we have already found. Okay, so let me just say this is 52 MLD is what you're getting as the coincident maximum hourly maximum daily draft. So 52 and correct. So whatever you got here before was this can be around 34. Yeah, I'll give you the values here. Sorry. So this is around 34, and this one I think this is not the, oh, pen stopped working. Yeah, so this is not the value. I mean, we get it as 52. So 52, what I've written below, that is the actual value you're getting. So essentially, after that, when we are comparing the maximum hourly draft, you will get two values. So one will be this 34 plus 52. That will be the first one, daily draft plus fire demand. And the other comparison would be 51, which is your this one, the second one, which comes. So it is 2.12 million liters per hour. So that hour we will convert it into day because you need it to million liters per day. So when you convert it into day, you will get a value. And finally, you will take the maximum of that. So in this particular case, the first one, which is the maximum daily draft plus the fire demand, that becomes higher. But in some cases, the maximum hourly draft can also be high. So that value you will take. Sorry, my pen stopped working. That's why I'm not being able to write this. But I think you will be able to solve this. So, shall we go to the next question? Is this okay?
Yes, ma'am.
Yeah, okay. So let's go to the next question. Estimate the total fire demand for a small city with a population of 50,000 if two fires break out in a day and each fire lasts 2 hours. The discharge required for fighting each fire is given as 1000 liters per minute. So the population is 50,000. So as I said, if it is above 1 lakh only, we can use the formula that 3182 root P. But if it is less than 50,000, we'll have to calculate the total fire demand, like the number of fire, the volume, which is needed. So here the amount of water which is required. So there are two fires. So two, oh, we have two fires, and each fire is lasting for 2 hours. So 2 hours into 60, and each fire requires 1000 liters per minute. So 1000. So that's why we, for 2 hours, we'll have to continuously give 1000 liters per minute. And the total population in a small city. So, so this is what we have to find. We have to find the discharge required for fighting each fire. Okay, so usually we find the discharge per capita, like for one per, the discharge final answer would be liters per LPCD, liters per capita per day. So for 50,000 people, we'll have to divide it by 50,000. Now, why in this question it's a bit confusing is because I didn't put the option. So in the option, LPCD will be there. If when LPCD is there, then we know that we will have to divide it by 50,000. Or if the option is given liters per day, then we need not do the division. So then we need not do this. We can just simply stop it at here. But if it is given, so the catch over here is we need to look at the option and then see the unit in which they have asked the fire demand in. So yeah, so this is an easy calculation. Let's not do that. Let's go to the next question. Yeah, this is a very, again, this is another important question which from exam point of view, from all question papers I've seen this question, so it's a very important question. Question 11. From a clear water reservoir 10-meter deep and maximum water level of 60 meters, water is to be pumped to an elevated reservoir 120 meters at a constant rate of 6,000 liters per hour. The distance is 500 meters. Calculate the brake horsepower to find power of the pump. Assume the economic diameter of rising main as 0.396 meters and F is given and efficiency is given as 90%. So, yes. Now, what do we essentially have over here? So we have some land and we have some water. So the water is somewhere here. And we have a pump or this one. So we first need to lift the water from here to here. So that depth is given to be 10 meters. That is, the water level is 10 meters deep. Now, maximum water level is 60 meters. So which means if this is the maximum, that is, if this is where the water level is there right now. If this water rises and it reaches over here, this will be 60 meters. That is what they mean by maximum maximum water level at 60 meters. The depth of this one is 60 meters. That is, it cannot go beyond that because that is the surface which we have. Now, water is to be pumped to an elevated reservoir at 120 meters height at a constant rate of. So this is the height. So distance is given later. So this is height which is given. So which means I have an elevated reservoir somewhere over here. And this height, so mind it, where people go wrong is people usually take this height to be 120. No, but if the question says that if the water level is given as six, like if the water level is given, and then if the height of the reservoir is given, that means you're starting from the base of the water. So this is 120 meters. So which means this one will also be 60 meters because 120 minus 60, this is 60 meters. So this is 60 meters. And this distance from this pump to this is given to be 500 meters. And this rate of pumping is given to be 6,000 liters per hour. Now we've been asked to find the brake horsepower of the pump. So why brake horsepower? So we know what is water horsepower. So water horsepower is W into what is it? Efficiency. No, in this one efficiency is not there. Let me just take that formula. Yeah. So, yeah, this is W into Q into H. So, Q is the volume of water which will be supplied. H is the head. So, head, in the beginning we discussed. So, the head loss due to all three factors we need to consider. So, the total head due to suction. So, to lift this water up to this point is a head due to suction. Then there's head due to discharge, which is head for discharge, which means from here to pump to this height, this is head for discharge, and then to transport it to this distance, that is head for friction. So all the three heads together, so HS plus HD plus HF, that is this H. And Q is the total pumping, so this is 66. So that is already given in the question. But it's given in what? Liters per hour. So to use in this formula, we will have to do some conversion. We'll have to make it into meter cube per second. That will be the only thing for Q. And W is the density of water, which is 1000. 1000 is the density of water. So this is water horsepower. Now, this one, brake horsepower. Brake horsepower is equal to water horsepower divided by the efficiency. And for unit conversion, we use 75 into the efficiency. So that's a conversion factor that we are using. So let's do this question now. Let's first we will find the head loss. So head loss, as I said, it's for suction. So this is 10 meters. So 10 meters plus head to pump it up, that is 60. So that is 60 plus HF. HF we need to find. So to find HF, we will use our old, the previous formula which we use here. That I'm forgetting the name of the formula. This one, F dash L V square by 2GD. We did a lot of problems using this. So to do this, F dash is what is given. Now F dash is equal to 4 times F. So in the F is what is given in the question, but the formula requires F dash. So we will use F dash is equal to 4 times F. So that is 4 into F into L into the other formula which we derived in today's class, Q square divided by 2 into 3.1 or pi. Let me write it as pi by 4 the whole square into d raised to 5. We derived this formula, so we will use the formula directly right now. So let's substitute 4 into L is a distance to which is 500 meters into Q is what is given in the question. Oh yeah, so before we use Q, we need to do that conversion. So Q is given as 6 lakh liters per hour. Can we convert it into meter cube per second? So that would be divided by 3600 in minus 1000. So this, yeah, so this 1000 would go, sorry, not divided by 1000 for converting into meter cube, then again divided by 3600 to convert hours to meter. So that comes out to around 1.67 meter cube per second. So yeah, meter cube per second. So we can put that over here. This would be 1.67 meter, sorry, 1.67 the whole square. You can check my value. No, it's not 1.67. It's 0.167. Yeah, 0.167 the whole square divided by 2 into 3.14 divided by 4 the whole square into d. What is d now? D is, yeah, as assume economic diameter is 0.396. So 0.396. Now, in this question, D is given, but in assignment, we did one question where D is not given. Partha says Q is 0.185, no, 0.167 it would be, not 0.185. Yeah, so if D was not given again, just to deviate a bit, we'll have to use Layer's formula in order to find D, which gives that D is around 0.96 times and 1.0, again, I'm forgetting the formula, but yeah, you can just refer. Layer's formula is what we had used in order to find D, if D is not given in the question. So, but for such complicated questions, maybe D will be given. But assignment, we had a question where we use Layer's formula in order to find D. So let's go. So this is 0.396. Yeah, so now if you solve this, yeah, we just need to solve it. It's direct solving. So that works out to around 4.742 meters, the head. So now our total head will be, so instead of this, we can add 4.742. So that would be 74.742. That would be the head now. Now let's go to our brake horsepower. Brake horsepower is equal to, so 1000, that is the density of water, into our Q value, which is 0.167, into the head, which is 74.42. 74 point, what did I write? 742. 742. Yeah, divided by 75, which is a conversion factor, into the efficiency. What is efficiency? Efficiency of the pump is 90%. So here efficiency of pump is given, so directly we can take 90%. Sometimes they will give efficiency of the motor is 80% and efficiency of the pump is 90%. In that case, we'll have to multiply like efficiency of the pump into efficiency of the motor in order to get the final efficiency. So this is not needed over here, but just to give you a hint, if both are given, you'll have to multiply it. So this is efficiency, so 90%. Okay. So that works out to around 184.81. This is the answer. Okay. Let's go to our final question. Do you have time? We can discuss the final question, right?
Yes, ma'am.
Yeah, okay. So calculate the rainfall intensity using empirical formula for a storm of 10-minute duration in the absence of rainfall record. So we have been asked to find the rainfall intensity. Which formula will we use over here? Do you remember? So we learned a formula, something like I is equal to,
20.4
very good, very good, 25.4.
into A by T plus B.
Yes, correct. By T plus B. So what is A and B now?
The constants.
Is the A and B are the coefficient, ma'am.
Yeah, so what will be the value? So A is equal to 30 and B is equal to 10 if the duration, which is T, of storm lies between 5 minutes and 20 minutes. And A is equal to 40 and B is equal to 20 if the duration lies between 20 to 100 minutes. So in this particular case, it's given as 10 minutes. So we can go with this one. A is equal to 30 and B is equal to 10. So I is equal to 25.4 into 30 divided by 10 plus 10. So yeah, it's a simple calculation.
38.1.
Very good. 38.1. So 38.1, that's there in the option C, 38.1. Okay. So that's all for the numerical part. I think I've covered almost all the numericals which we have discussed in the assignment and some additional. So if you're preparing for the exam, you can assignment questions, definitely you can go through the assignment questions, but most of the assignment questions again we have revised over here. Important questions also which are seen in most of the question papers, I've marked those three questions are really important, that will be there. The previous question is also the one which we did. This is also the brake horsepower one is also important because this is also usually asked and people go wrong in this conversion of water horsepower and brake horsepower, so that you can keep in mind. So yeah, do you have any doubts in any of the numericals or theory or anything?
Ma'am, good evening, ma'am.
Yeah.
Roughly how much questions will be there, ma'am? Like
uh,
in part A, part B, like
so did you not get the this one exam pattern, question paper pattern something?
Multiple choice.
not yet, ma'am.
You were just told that it's multiple choice question, is it?
Yes, ma'am. Yes, ma'am.
Oh, okay.
I know about that because I have attended another exam. So, but I
Uh-huh.
don't know how much questions will be there
Okay, that
for
part
this
even I
course.
don't know because actually exam is set by a different team. So I don't know what that would be. All I know is that yes, it'd be multiple choice. And last year there were these 5 mark questions and all, like the problems which we did. So one problem had too many different parts, right? So which means each question was a 5 mark question. But this time that's not there. Everything is the same evaluation, like same multiple choice type. So I don't know how they're gonna separate it as part A, part B. Also that part also I don't know. So. But I guess it'll be very similar to the assignment questions itself, and all questions will be of the same mark also, like either 1 mark or 2 mark. That's all I know. So maybe you can put it in the discussion forum if the other NPTEL team who's setting the question paper, if they are, they can probably clarify it. But I don't know this. Any other doubts?
No, ma'am.
No, ma'am.
Okay, great. So that's it. So thank you both. Thank you both for joining this extra session and joining the other sessions also and being very interactive. It's been good because talking to a blank screen is very difficult, but when you interact, it really helped me also explain better. And yeah, so I've just put my details over here. So in case you have any doubts or anything or for future contact, you can always keep in touch if needed. Any doubts you can put in the discussion forum, or if it's anything very much particular to, or you don't want to put in the discussion forum, you can reach out to me also. So yeah, so that's all. So thank you. I think we can say goodbye to this session NPTEL, I think 12-week course, right? So when is your exam?
28th, ma'am.
28th,
28th
so
of
10 more
October.
days, huh? So you can prepare. I think 10 days preparation would be good. So, I mean, just before we end, I just want to know about both of you. So, Aishwarya, can you just tell what do you do, where are you from and all?
I'm an architect, ma'am.
Okay.
I did my UG PG from TCE, ma'am, Madurai.
Okay.
So
Okay.
I'm as well working as an assistant professor for about 5 years now in TCE.
Okay. Oh,
And
that's great.
also before that, I had 8 years of experience in the industry also. So
Okay.
basically, I have like 13, 14 years of experience.
Wow, that's great. That's great. Interesting. So this course, is it, are you teaching this course or were you working as a planner before?
No, ma'am. I just wanted to know more about this sanitation and other.
Okay.
Well, last time I took a different NPTEL course.
Okay. Okay.
Then I wanted to learn this.
That's good. That's great. So you are an architect itself, right? Or an architect planner?
No, I'm an architect.
Okay. Okay. Great. Very good. Yeah, thank you. And Partha, I think I mean, initially I remember, but maybe for Aishwarya also, can you speak a few words about yourself?
Sure, ma'am. I'm doing my thing is civil. I'm from
Oh,
civil.
okay,
I did my UG in Hindustan University, Chennai,
okay, okay,
and currently doing my master's in environmental engineering in Anna University.
okay, okay, great. That's
So
nice.
that's why I could relate this course to my PG course.
Yes,
Like
yes, yes.
three, four different courses I've been mapped as a single 6 month. I mean, 12-week course. So
Oh,
I felt this will be the course which I can learn this in this semester.
okay. Are you writing
It was
other
not initially. It was
NPTEL
not
exams
said
or
by
not?
university. Yes, ma'am.
Sorry, what did you ask?
No, I didn't ask anything, ma'am.
Oh, okay. So I was asking, are you attending other NPTEL courses also? This
I did a course like sustainable engineering and life cycle analysis. I did that
okay,
course, ma'am,
okay, okay. That was
recently.
last semester, no?
So I'm doing this. No, this semester only.
This semester
Like
itself. Oh, okay,
parallel, I was doing.
okay, okay, great.
That's fine. When I got cleared that course, just a
Oh, congrats.
decent percentage. Thanks, sir. So next, for next semester, I'll be doing another course in urbanity utility planning. There is another course. I don't remember the exact course name,
Okay,
uh, but it starts with urban development something.
okay.
Transportation. Urban.
So
Transportation is this
trying to
semester,
do that
this
also.
course, this time itself. Next time we have one on this one waste. Pandit Professor Pandit itself. Pandit's one course is also there. So that was on again waste treatment and all. I think I'm not very sure. Yeah. Okay.
Yes, ma'am. That's why I forgot the course. The short form was UDGM or UGDM. I don't know what abbreviation of the course name,
Ha ha ha. Fine,
but
fine.
I
Yeah.
saw that.
Good. Good. It's very good that NPTEL courses are actually very useful because we go into a lot of details, right? So uh, for practical applications also, it is very useful. Okay. So yeah,
Yes,
so
ma'am.
one thing common, I think all of us have studied in Tamil Nadu. Because Aishwarya also said she studied in Madurai. You're from Chennai. I studied my bachelor's in
Okay.
architecture from NIT Trichy. So again, in Tamil Nadu itself. So we have that root
Okay, ma'am.
there.
Great.
Yeah. Okay, so it was nice to meet you all through this platform also. And we had a wonderful, I hope you also enjoyed the sessions. I definitely enjoyed the sessions with you all. So thank you once again. So let's call it a day and the final of this 12-week course. Thank you.
Sure. Sure, ma'am. Thank you.
Yes, ma'am. Thank you so much, ma'am.
Yeah.
Thank
Bye.
you.
Bye. Good night. All the best for your exams.
Thank you so much, ma'am. Thank you.
Thank you, ma'am. Thank you.